this presentation. And most importantly, we have Joe Pfeiffer from KCI, who has agreed to shrink down a 3-day workshop into a 35-minute webinar, since we all know you are very busy. It's our goal that after this presentation today, you'll have a better understanding of the basics of a stable stream channel, issues that arise when natural processes are interrupted, and solutions to common problems like trees falling into the river. So today we're joined with Mr. Pfeiffer, who is a regional practice leader for KCI's resource management discipline with 34 years of experience in ecological restoration. Since joining KCI in 1988, he has been responsible for coordinating all aspects of environmental engineering projects for public and private clients. He uses his diverse background to integrate engineering and environmental planning to develop a comprehensive project approach, facilitating working relationships among stakeholders and design teams. Mr. Pfeiffer has been responsible for wetland and stream restoration and design, watershed planning, bioengineering design, NPDES permit processing, water quality analysis, biological inventories, BMP identification and development, and wetland delineation, mitigation, and permitting. Finally, he holds a Master of Arts in Physical Geography and Environmental Planning and a bachelor's in natural science. So clearly Joe is an expert, and we are grateful that he is here today to share some of his wisdom with us. And without further ado, I'm going to turn it over to Joe.
Thanks, Christy. Thanks for taking your time and showing up tonight and hearing what I have to say. Dave approached me with basically trying to provide some educational context to some of the common problems we have in the urbanized channels with wooden debris and many other things that kind of go on there. And it's a relatively complicated subject matter. So one of the things I'm going to do here, and I'm going to basically kind of do this in a couple different parts. So I'm going to kind of cover this in a couple different places. In order to basically kind of really understand a lot of this stuff, we kind of have to back up and understand rivers and streams. So I do a section on Fluvial Geomorphology 101, basically crushing 4 years of grad school down into 20 slides. It's a little bit cryptic, but it gets the kind of the message across on some of that. Then talk a little bit about some of the roles that we have for trees in the river, what they do and why they're there and what their benefits are. How we can manage rivers, especially in urban environments, to kind of maximize benefit in both sides of things. And then also kind of how we use trees in river management to kind of make things work better. So start off with fluvial geomorphology. A lot of, it's kind of a big word and looks like a category on Jeopardy, but it's really pretty straightforward. Fluvial meaning with water, geo meaning earth, and morphology meaning the change. So in essence, it's the study and development of the evolution of streams and rivers in response to the climate, hydrology, watershed, geologic province, and the landforms they create as a result of water and sediment transport. It's kind of a mouthful, but it's basically the processes by which streams form and modify and change themselves on the landscape through time. It's an actual significant science. It's the most basic component of it is the drainage basin. It's basically what are the boundaries by which water runs to a common point. There's the stream is the common point, and there's a discharge point in the end. So everything that happens within that area is considered the drainage basin, and it's all controlled by what's within that boundary and the hydrologic cycle that basically acts upon that boundary. The hydrologic cycle is basically any of the regional climatic processes that are at work, and that's basically water evaporating out of the ocean or out of lakes, basically going in the cloud formation, creating precipitation, runs on the ground, that runs off the surface into streams and lakes, and then we're back in the infiltration in the soil and percolates into the groundwater. That's all part of the hydrologic cycle. They all integrate with each other as part of that, and they all act on that basin to basically form a relatively process by which everything is regulated by. When you have the hydrologic cycle, when you have precipitation within the basins, it basically have what's called a hydrologic response. That hydrologic response is a couple different forms. You have precipitation that falls on the ground. Some of that precipitation infiltrates and goes back into the groundwater, and you have the first very tenth or quarter inch of it. The next pieces of it basically go into the shallow or subsurface flow, which is in the leaf litter or in the material that's in between there, and then runs towards the stream channels. Then once you get beyond that, then you just have overland flow where you have water running off of the surface and running into the stream channel, and it all basically either goes into the water table or back into the stream itself to basically create a flow process in that hydrologic cycle. That's kind of the most kind of the critical part of the basis of where the streams operate. So that process of precipitation and transport across the land surface forms a basin hydrograph. Now we're starting to get a little bit more into the complications of things. So you have to think about it over time, where when you have a rainfall event, you have a point in which you have a rising limb, or basically the water is starting to basically fall on the surface and start generating runoff. Initially, you have that point where it just goes into the ground, but the more you have, then it creates a runoff. You get a maximum point of stream flow, basically about halfway through your rainfall event, and then it slowly kind of tails off back to the base low conditions, and it's considered your hydrograph. That is the heartbeat, if you will, of a stream's function within the landscape. The stream, as the process of doing that, moves sediment from the system, from the top of the system to the bottom of the system. Now, one thing this is kind of one of the key points in understanding streams. They are conveyor belts. They have a mission in life. Their mission in life is to make everything flat, to move everything from the top of the watershed to the bottom of the watershed. They don't like the Rocky Mountains or the Appalachians. They want them flat as a pancake. So their mission in life is used through gravity is to move that material downstream. The rate in which it does that is dependent on all those basin conditions, hydraulic cycle, and all those things. But at some point they've reached kind of an equilibrium there. But that movement in the system is important because the sediment basically consumes energy from the channel, from the water flow, and basically then moves that material downstream slowly over time. But by no peck about it, there's nothing we can do to stop it. There is a sediment transport conveyor belt which exists in every channel, even ones that are perfectly stable. It's such an accurate thing. We actually can derive this equation to basically predict how much material is moving through that system. So we can derive it now, but I would think that would be rather annoying. So I'll just want to show you the equation to recognize it does actually exist. There are physics behind it, and it's very predictable how much sediment will move through a system based on those conditions. So it is a very, very accurate means of basically estimating sediment transport in the system. So we start looking at over time how these channels move this sediment down through the system. So this is I'm going to spend a little time on this because this is an important graph, but it's also a little bit on the complicated side. So we're going to break it down into pieces. So if you look at this first line here, and can you see my cursor on the screen? I don't know if you can. Okay, good. So this is the frequency curve. So this is the frequency of rainfall events over time. So this, when you look at this may be a, once a week event. This right here is probably your every 3-month event. As you keep going on down here, this is the event that happens like maybe once every 2 years. And then all the way out here is the event that happens once every 100 years. So it's a frequency of events and by volume and how often they occur. So you have a lot more storms that happen every 3 months and say a ½ inch of rainfall that happen on a regular basis than the 15 inches of rainfall you get when you get a 100-year storm event. The sediment discharge rating curve is here. This is how much sediment is moved during those time periods. So you can see from this is that all those little regular storms, every couple weeks or a month or so, they've really moved very little sediment through the system. The 100-year storm all the way out here moves a lot of the most sediment through the system, but it only happens every 100 years. So that, once every 100 years, it's moving a big chunk. This here, which we call the effective discharge, is that rainfall event that occurs, say, every 1.2 to 2 years. So it varies by locality depending on the climate, but it's always on that same recurrence interval. It moves a volume of sediment that because it occurs on a regular basis, you look at this line here, which is the magnitude of both the sediment discharge and the frequency of recurrence. And so the most sediment is moved over time on storms that occur between 1.2 and 2 years. the volume of sediment, that's where your most sediment is moved. And that's why we call that effective discharge often the stream forming storm. That is the storm, or that's the return interval that has the most influence on how streams function in the landscape and basically evolve over time. So I'm going to go through a couple bits and pieces here because there's some terminology just to kind of be familiar with as you're talking about streams. So if you hear someone talking about a thaw wag is actually the flow course of the channel. So it's actually the dominant point in the channel where water flows. It's not the middle or the center of the channel, but it's actually the point where most of the velocity is in the channel. So in a sinuous channel, like this example here, it would come on the outside of the meander bend, the deepest part here, it would go back across the center here, and it would come back, go across to the outer side here. That's the fall wag of the channel. Within the channel, there are features called riffles, which are the intermediate points between two pools. That's a riffle. A run basically comes out of a riffle, entering into a pool. So it's that little bit deeper section right before you get into the deepest spot. Then you have a pool. You glide out of the pool into the next riffle, and then you're back into the riffle again. So those are the basic sequential features that you have within a channel. Those sequences are important for both how the channel functions biologically, but also how it processes and moves sediment through the system. You also have what's called sinuosity, which is the amount of curvature within the channel, how much it basically wiggles around within its floodplain. The belt width being the outer width of between the outer meander bend here and over here. So that's your linear foot difference. These are the things these are measurements we take to try to understand and classify channels so that we can understand what they are and what they're going to do. The other major component is we consider the cross-sectional area. So the cross-section area, so you're looking at a cross-section of the channel itself, and you can see this where we call this bankful. It's that dominant effective discharge. That's the basically point where you have the maximum amount of depth and shear or energy being placed on the sediments in the bottom to move that conveyor belt along. And that occurs kind of at that bankful depth. Once you start getting up here, the volume of water, which is out here on the floodplain, basically it increases in volume without increasing a whole lot in depth. So therefore, you don't have as much ability to kind of push that material along the bottom. But the cross-sectional area of the channel is important, again, from a sediment transport standpoint. So when you basically have all of these things in balance, when you have the amount of water that's coming into the system equivalent to the amount of sediment that the system is producing, and that the shape of the channel and its sinuosity and its cross-sectional area, when they're all in balance, you have what's called an equilibrium condition in the system. A lot of this refers back to these channels don't evolve, over 2 years. These aren't even 500 years. These systems evolve in equilibrium condition over the past 5,000 years as all these factors have been applied to the basin and have moved forward over time. So you come up with this equilibrium condition, and in those conditions, the river is happy and satisfied. If you add more water, then you basically change that equilibrium condition, and something has to change in the stream channel, whether it's the sinuosity, whether or not it's the cross-sectional area, something changes. And so this is kind of the balancing act in terms of what we call river mechanics of a channel and equilibrium system. And that's kind of the ultimate, the only place you're going to see that is in rural Alaska or, Rocky Mountains where no one's ever touched or built anything. And as a society today, that's just not the case. But it's important to understand that that condition does exist because that is the condition that any channel, no matter where it is, wants to achieve at some point in time. That's what it's trying to do. That equilibrium condition you can define as it's the ability of the stream over time in the present climate to transport the flows and sediment produced by its watershed in such a manner that the stream maintains its pattern, planform, and profile without aggrading or degrading. Aggrading means it's depositing sediment within its channel, and degrading means it's scouring water out of the bottom of its channel. That's considered an equilibrium condition, and that's really what we strive for, because when you have an equilibrium condition, you have the best of everything. You have the best ability to transport water and move it through the system. You have the best ability to create ecological function and balance. That is kind of the optimum piece. It's a difficult thing to achieve, but that's what the objective is. So all these things are affected though by influencing factors. So when you look at a basin, any basin, you have different land uses. You have, whether it's forest or agriculture or urban, they have different slopes depending on where they are within the system. Have they been glaciated or have they not been glaciated? The types of valleys that the channel is found in, and the climate. Is it in a coastal climate? Is it, is it a 5 inches of rainfall a year climate, or is it in a 30 inches of rainfall climate? And then the erodibility of that material and that sediment that's in the basin, how it moves forward. And it doesn't matter. I've heard people say, well, yeah, but that's not, it doesn't work here. That only works where this other person did this work over here. It doesn't matter. Gravity and sediment are the basically major factors of this whole process here, and everything revolves around them. It's so consistent that you can even look at them when they look at Mars and they're looking at the features up there, they can identify fluvial features and identify what historic conditions likely were by looking at what features have formed within that on the planet's surface. That's how consistent it is. To that point, we were able to take and then classify stream channels into about 8 different classifications. So everywhere from A up to G. They all have different characteristics. They're all different slopes. So we literally can go out and measure the characteristics of a channel and say which category it falls into based on a whole variety. There's 15 different measurements that wind up into this, and I'm kind of shortcutting it just for our time considerations. But it's consistent enough that we can classify it, and with that, we can really understand what the channel is doing and where it's kind of going to in the long run. Now, all of this is prefaced on a condition of where we have kind of a natural condition out there. So in a natural condition, and this is non-pre-development before mankind, you would generally have about, in a basin, you'd have 10% of the water would run off on any given event. You'd have 40% of it that would go through out of the system through evaporation. You have 25% for shallow infiltration back into the ground, and 25% back into the groundwater. Now that's a normal, natural condition, unimpeded system. That creates this hydrograph that I showed you before, a very clean hydrograph in terms of how things work and how they go within the system over time. That results in what we call natural stability. So that's the ability for a channel to basically form itself, create that balance, move that sediment through the material without really changing through time. That's kind of our basis for comparison. So like I said, it's not, you don't see that too often, but that's our basis for comparison that we use when we look at what has to happen. That's a stable channel. However, for the most part today, any type of areas where we have any type of development, we have infrastructure, our needs as society to basically continue to operate, everything has changed. So now instead of having 10% runoff on a given event, we have 55% runoff. We maybe have 30% evaporation. We have 10% going to shallow infiltration, maybe 5% going into deep infiltration. So that changes that basic characteristic. Remember I showed you that kind of teeter tot where you have water on one side and sediment on the other side? Now I've got a lot more water. So that changes the situation. So what happens is when you look at a hydrograph that's created from that, you changed everything. So now you have this huge peak of soil water flows basically rushing off of the landscape, where down here, this was what it was initially, this nice bell curve. And so now you have a much steeper with more water coming out early and then dying off very quickly. That means that the channel wants to basically change. You go from a stable condition where it has the amount of sediment it's moving, and that conveyor belt's kind of pumping away. And now all of a sudden you turn the conveyor up to Lucille Ball speed, and things are flying out down the other end. That sediment's got to come from someplace. It's going to be, it's what we call hungry water. It basically, you got energy and you basically need to use it. A lot of times, what I'll describe it as, imagine a roller coaster, gravity roller coaster. Basically, everybody's on board to get to the top of that first hill, and they set it free, and it goes down, and there's enough energy to take it up to the next hill and around the corner and back all the way back to the beginning of the basis. Now, you put 50 more people on that, and it's got too much weight. When it hits that top of that second hill, it's going to keep going straight because it's out of proportion with what it's got going on. You put not enough people on it, maybe it doesn't have enough energy to get to the next hill and make the turn. So the roller coaster being the water and the sediment being the people in the roller coaster. It affects the ability of the channel to basically function the way it has historically reached a stable situation. So when we have that change in hydrology, it creates a evolutionary process in the channel. So in cross section, if you look at this, this is the stable channel. You have a channel, you have a floodplain in there, water comes up and down, it's enough to move its sediment through, get its water out there, but then you start adding more water. Well, now you have a higher velocity. So the channel wants to start down cutting. You start seeing this occur in a lot of urban channels. You start down cutting. The first thing it wants to do is dig deeper. The reason being is that deeper channel has more shear stress by volume of water in it to move more sediment. So it's taking all that sediment that's eroding from that additional water because it's the energy, it's fast, and it's pushing it down the channel. As that keeps occurring, you basically start getting instability in the sides. And this is where you start running into problems with trees, it running into infrastructure, and it starts beating off of the sides of the channel. And the channel tries to widen itself out, trying to basically redefine what its stable condition is within the area it has to work with. And that's where you start seeing problems in channel. A lot of channels we see in urban areas are in this condition. They're in this point where they're widening and they're chewing into things, and it's causing problems with things collapsing into the channel, trees, infrastructure problems, everything else. Ultimately, the channel will reach a new stable condition at a lower elevation with a lesser slope so that it doesn't have as much velocity, and it's in balance back again now with what material and the new climate or the new hydrology the system has and the amount of sediment it has to work with. So it is a very clear process that follows. We can predict this process and show it, in cross section. So here's a basic stable channel. As it starts, it's called an E4, which is kind of the most stable channel there is. Then basically you start getting the flow to it. Well, it starts to migrate and you start getting this kind of channel formation here. So you have this wide kind of point bar meandering channel. But then it keeps migrating even more and it starts beating off of the sides of the channel here. So then it changes to a G4 here, which is basically this kind of big flat cutout channel. And that channel straightens out. You get midpoint bars. I'm sure you've seen these channels where you've got piles of sediment in the middle of the channel, water going around it. That's a G4 or F4 channel going into it. That keeps occurring over time, but then it'll start, once it gets to the point where it's taking all this stuff from left and right side, and it'll restart figuring out how to basically be happy within that new, we call meander belt width here to here. And it'll start re-meandering and changing its slope and fine adjusting for its conditions. And then ultimately going back to the condition it started from in a stable condition, just at a lower elevation. It's a very defined process, and we can look at it. Most of the urban channels we see these days are somewhere in this condition here. They're in this little section of the thing here. So they're between two stable states. So instability is that basically change in the channels as a result of the change in flows or sediment that's being provided to it. And that's what creates that interim state condition that's out there as a result. So just to review that a little bit. So this is kind of my Geo 101 review. So rivers are an outward extension of their physical environment. It's based off of the basin they're in, the type of materials, and then the climate that they're into in that location. When they're in equilibrium, they don't aggrade or degrade. They are just happy kind of moving their sediment down river and basically dumping it at its lowest point. That's what they do. Changes in that system create that instability that results in a channel evolution that's in between two interim states of stability as the channel tries to go from one to the other. So and that's a 20-minute nutshell of kind of how the systems work in general. Now, the next thing is, so trees are often some of the problems that are identified in a lot of these systems. So what are the role of trees? There's really four basic roles that you really see of trees within in how they function within the system: bank stabilization, habitat flow and diversity, sediment transport and retention, and vertical and lateral evolution. Those are the four basic things that you see with trees. Now, bank stabilization is pretty straightforward. The roots themselves, when they're on a bank, they provide resistance to near bank shear stress. So the channel wanting to kind of widen out. The roots act like rebar in concrete and hold things in place. And so they help stabilize. We talk about that natural stability piece. Well, part of that is basically you have stable banks. So if there is a little bit of adjustment or you have a year where it's super wet or super dry, those trees kind of help hold everything and keep it stable while they're in that equilibrium condition and kind of act like a buffer to allow that to occur. So the vegetation in general, whether it's trees, brush, or any type of woody vegetation, are very important to basically bank stabilization. Debris jams themselves, even when they do come into the thing from natural falling of trees, they basically help armor banks. They flow up against, and they'll actually take and armor a bank so that it can't be eroded. So they act kind of as like an erosion blanket at times. Now, this doesn't mean that excess amounts of them don't create problems, but in the system as they function in a kind of a stabilized system, that's one of their major purposes. They also create a lot of habitat flow, diversity, and water quality. So you imagine from an ecological context, you just have a basically plain flat slate desert. There's not a whole lot of diversity in there, so therefore you don't have a whole lot of biological activity going on. Anytime you can add diversity to a system, you increase the ability of that system to provide habitat and water quality benefits. So the woody debris in a channel, leaf packs, fallen logs, they create the basis of the food chain in most of these stream systems. That's the macroinvertebrates and the small bugs that are basically chewing and eating them. They're carbon sources, so they basically become food. And then in turn, that creates habitat for fish. And then basically the whole basic building blocks of the entire food chain is built up from that. They also established seams and upwelling. So if you have a seam of water, that's where you have a quick change of flow. Water dies out in front and basically then rushes around the tree branch. You can see in this picture here, you can see a little bit of water rushing around this side over here. That change in flow also creates mixing and plunging and upwelling in the water. That does a couple different things. Those upwellings and those mixings basically keep the water on the bottom from stagnating. It drives water down into either leaf packs on the bottom or the gravel or sand on the bottom and keeps it oxygenated and allows microbes in those subsurface areas to kind of digest and take out nutrients out of the system. They basically promotes oxygenation, and it basically creates the basis by which the chemistry of this channel basically can continue to function. So it's more important than just simply having some ecological things. They actually have chemical influences on how the channel processes what's being provided to it from a nutrients or pollutant standpoint over a period of time. You also have sediment transport and retention. So you can imagine that any type of change in the system has an ability to can block the movement of that conveyor belt, and it changes things around. It helps it basically, either preserve stream feature, whether it's riffles or pools. In a riffle, you might have a log that basically is in the channel that holds that riffle in place so that it doesn't just kind of want to wash out over time. Dead roots or even tree branches that get lodged in the bottom of pools create turbulence within those pools as you have flow coming through them to continue to move the sediment out of the pool so that you don't have sediments that fill up with or pools that fill up with sediment and then no longer become pools, which are a pretty important ecological component of the system. So they have the ability to both help hold sediment back, and which is the bed load, as well as move sediment forward. And it also, you can get deposition of excessive sediment. So these are all kind of the buffer factors that basically that they provide. They also create vertical and lateral evolution. So when I was showing you an evolutionary chart where you can basically say, I told you how the channel cuts down through the system first, and then it wants to bounce off the sides. They can cause and create that. So in that context, they're a very important initial evolutionary component of a channel basically changing from one stability realm to another stability realm. So if you have a tree that's undercut and falls into the river, water always turns 90 degrees to a object in the channel like that. So if you have a tree that falls and goes downstream, now it's pointing downstream. When that upstream water strikes it, it turns 90 degrees and goes right into the bank. So it accelerates that rate of bank erosion, which accelerates the rate in which it's trying to reach that equilibrium point. It makes a mess at the same time. You see the picture up there, and that's a very common overwidened channel where it's just starting to kind of sort itself out. But when we're looking in the context of channel evolution, we're talking about some things that are evolving back to stability over 500 or 1,000 years. And the problem is we've changed so much of the basin characteristics in the past 200 years that it hasn't had a chance to keep up with it and do it slowly. So it's trying to do it all at once, and that creates us problems in the long run. So key things to take away from the role of trees is they are a natural component to system evolution. they are definitely a viable and beneficial component from basically helping the channel evolve into the next stable condition, but also provide really key roles in both habitat and water quality as it goes through that evolutionary process. So they are very significant components of the system overall. So we'll talk a little bit now about management of rivers and urban environments, and this is kind of some of the probably the most challenging stuff. And in the 25 to 30 years that I've been messing with channels, and it always seems that urban channels are the ones people want restored, this creates the biggest challenge because, you know, we have to basically balance between the societal needs and ecological value. And that's not saying that either one of them gets priority over the other. It's just simply a recognition that how we have to work with the system in order to basically be effective. So when you look at this picture here, this is a channel that we had worked on at one point in time with all of the constraints identified. Everything from suspended pipes to outfalls to paralleling to road crossings to you name it. You have this whole mixture of things because everybody likes to put stuff along stream corridors. So you have to work around that stuff to be able to kind of deal with it. Well, part of doing that is basically kind of understanding and managing the fluvial process. That whole Geomorph 101 section, the reason I did it was understand that there is a process. It is very definable and it is very understandable. So we have to try to manage and try to help it get back to that stability condition as soon as possible to maximize that functional value. And then finally, I'll talk about a little bit of what I call guerrilla tactics in the process of doing that. So our objective when we look at trying to manage urban channels is kind of what we call an intermediate stable state. We know it's between two realms of stability, one with historic 500 years ago level of stability to where it wants to get to for its changed conditions. So the process of trying to work with these and manage these channels is trying to recognize where it wants to be and how can you help it get there. Different ways you can go about doing that. Sometimes we literally come in and say, hey, we're going to basically restore this 5,000 foot channel, and we have to go in and figure out exactly where it wants to be 100 years from now and put it in that condition, and then it's stable again and all is good. Problem is that has a tendency to be rather expensive and basically is long-term process at 5,000 foot at a pop. But the other aspect of it is how do we manage it? How do we basically work with the system to try to help it along its way? That may mean that, yes, we need to take out some wood during the process because it's basically creating a challenge to infrastructure, but it may mean leaving other wood in because it isn't basically posing a problem and it's helping it seek that equilibrium condition over the long haul. So there's that balance point of understanding where it wants to be and then basically helping it get there either by active measures or by passive management measures. Then there's what I call guerrilla tactics. So this is, I've professed this for many years and called it restorative development and many other things, but basic understanding guerrilla tactics, how do you use your enemy's strengths against itself to help you? Well, when it comes to working with stream channels, that's where kind of wood comes into play. It has so many benefits and how it functions within the system. Learning how to work with it and use it as a means of helping it reach equilibrium without basically having to take it out has significant benefits moving forward. So it's first part of that is understanding the fluvial process, understanding the enemy, and then figuring out how to manage that as you move forward. So if you have a tree that falls in the channel and it's facing downstream, you know that it's going to erode the bank, and that may be one you want to pull out. If you have one that falls upstream, you know that that's going to push that water back to the center of the channel, and maybe that's a good thing. If you have an embankment that's blanketed with a debris jam, maybe that's okay to leave there because it's protecting that bank. So part of that is taking what the channel is giving you and trying to work with it along the way and make it basically a value to the process as opposed to basically just a wholesale removing and changing the system to basically meet a very common trapezoidal shape for one purpose of moving water. So that's a challenge that I think a lot of people should be thinking about as they're basically looking at their systems and how to best manage them. So these are a couple examples of where we've applied these types. We use log structures in stream restoration processes, and a lot of times these types of elements of these designs come from observing where we've seen these in natural channels, and then we try to replicate them back into a restored channel. These are all these are channel items that we have built as part of the restoration process. This is an embedded log grade control structure. So its intent is to keep the water from basically keeping it from down cutting and using those logs to basically hold grade. You can see how that log kind of holds material behind it so that it doesn't basically just kind of want to cut out if you do get a stronger storm in the long term. This is an embedded log vein whose design is to help move water around the corner and redirect it in a manner that we can control the amount of energy that's placed upon certain points in the channel. This is a woody brush toe. So this is a deformable feature that is basically built into the bank that basically allows it to create some turbulence so that there's a pool right underneath of that to basically keep it flushed out for habitat purposes, but at the same time protect the bank and allow vegetation to grow. Both the vegetation, in this case willows, that are all up here and here, can fold down in the event of a storm event, and the wood is somewhat deformable, which allows it to kind of adjust to a flow that may be putting upon it, but then come back to its condition and being dynamically stable in the process. This is another type of wood called live lip, which is similar to that woody toe, but it basically has more vegetation above it. The whole point of all of these is that we utilize vegetation and wood as part of processes to fix these channels, and we're doing it in a much more dictated way for very specific engineering purposes. But in any channel, when you have these conditions in there, they can be applied. The concepts can be applied and work with the channel to basically try to help it basically get to some closer level of stability, which is where it wants to get to. He is trying to know where it wants to get to so that you can help it get there. This is a log cascade riffle, which is it's hard to see here. It's a little bit brushy, but as you can tell, it's basically using that wood to basically help move material around. And anytime we do this, we're providing resilience to basically flows from erosion, we're providing habitat, and we're providing water quality benefits in the process. So they're very effective in doing all of those components. So summary points is, for this whole presentation, rivers evolve over time in response to changes in the system. It is a natural process. It's understandable, it's definable, and it's actually predictable as we go along. It's not a mystery. We may not like the answers we get when we do the numbers, but we can identify exactly what's going on with them and basically kind of get ahead of the game. The woody debris are an integral part of that river evolutionary process, both from the biological standpoint of being able to provide habitat and water quality benefits, but also from physical functions, because they are kind of the early guard in trying to help the channel basically change its condition to basically reach that stable state. So they're kind of the first thing that basically invokes that. And then, in general, rivers need to be managed as part of the evolutionary process, because, we have to have development, we have to have infrastructure, there are societal needs, there's no questions about that. We also have ecological needs. And it is very possible to balance those two by coming in and managing the systems and kind of in an equal share as they kind of try to get to that stable state and get to an ultimate endpoint. We've been kind of doing this work for better part of 30 years overall as an industry, be it in pure stream restoration or whether it being management or thing, and I'm speaking of the scientific community as a whole. And it's very conceivable and possible to basically be very effective in meeting both goals at the same time. So with that, I'm happy to open up the questions. I know I hit stuff kind of fast, but I'd be happy to try to interpret anything that I threw out there.
Well, Joe, I thought that was an amazing crash course into Stream 101 and all of the dynamics of a stream system. I will say, if you are heading out and you're not staying for the Q&A, thank you so much for attending. We have representation from 6 municipalities here, which is awesome, and I hope to see that number continue to go up in the future. Remember, Root-Pike Wind is always a resource for your municipality with issues with streams or flooding and anything you need. So with that said, either goodbye, or do you have any questions for Joe while he's here?
Hi, this is Nancy.
Hi.
Hi. So very, very interesting, Joe. I don't know if Christy told you or not, but I have multiple reasons for being here. One of them is I'm a village trustee in Mount Pleasant, and I am on the Stormwater Drainage Committee. And number two, I live on the Pike River. In fact, phase 9 of this Mount Pleasant project involved 20 acres of our farm that they acquired, and it's now this amazing ecosystem. And then I'm also professionally, I'm a land development consultant. So it's everything that this is also my like 6th or 7th degree that I would have liked to have gotten, natural resource and watershed study, because it's fascinating and it's so important. And what you were able to explain in this, I probably have so many questions that I don't really have any questions, but now I see what has been done in the Pike. I see the logs I kept wondering, why did they throw those trees back in there? Somebody's got to get those out of there. Thinking that typically when we're working with stormwater in a subdivision situation, we want to keep all debris out, no trees planted, so it's very different on a stormwater management, urban design level than a natural ecosystem. And you've really opened my eyes to that. And so I can't thank you enough. Are your slides available for this?
Yes, I think they're going to post it, and Christy, you can turn them into notes pages or whatever you want. That's fine.
Yeah, that would be great. I'd love to copy print some of your examples of the different techniques and so forth. So I really don't know that I have any questions other than thank you so much, and very effective. And I guess the question would be, if you're in a municipality and you have a large river or a small river or a body of water that you want to have studied, and you want to have someone come look at because you see fallen logs in it and you're not sure, are these good logs or bad logs? Is Root-Win a place we can go to get that kind of assistance, to have them come out and do cursory evaluations?
I'll let Root-Win speak to that in terms of what they can and can't provide. I will say that there are many people out there that are specialists in streams. We do that, but there are also many organizations and companies, Trout Unlimited, both for-profit and nonprofit, that have the expertise to basically provide those types of assessment services.
We aren't engineers at Root-Pike Wind, but we can hook you up with the right people. Even if you just sent us some pictures, we can get you the information that you need and assist in any way you can. And we can.
Lots of resources then.
I see we have a question from District Alderman, 6 Alderman.
Yes, on the same piggyback that, I guess I would question how you figure out what a good log and a bad log is. I have the Root River in my backyard, and I travel up and down, either walking or biking or ride, either way, I'm up and down the river all the time, and I'm always seeing trees down. And I've always seen them as a hindrance, but as you explain it, they can be beneficial. So I guess like the previous question is, how do you figure out which one's which? And how do you balance, especially when you deal with the river, like the Root River that can be seen as a recreational river? How do you balance the recreational aspect with the environmental aspect?
Well, I'll do two things. First of all, the complexity of determining what's a good log and what's a bad log, or good condition, bad condition, varies with the size of the system. So if you have a real small first order tributary, there's not a whole lot of power there. So you can have a huge margin of error and basically think it's a good log when it's a bad log, and it doesn't really, impact a whole lot. But if you have something the size of the Root River, where you can have one log that basically you kind of need to know what the channel's doing. And this is a lot of times I'll use the medical analogy. The work that we do, it's like being a doctor to a certain extent. You kind of read the patient's symptoms, and they draw from experience and basically scientific research to basically kind of understand what the proper cure is or the treatment is for the symptom. So in a nutshell, logs in particular, and I'm mainly thinking about logs that have fallen in off the bank. If a log basically falls in and it's facing upstream, it becomes what we call a vein. So it's lower in the center of the water and it's higher on the bank. So as water strikes that log, it turns 90 degrees and pushes it out back into the flow, the main flow of the river, and pushes it away from the bank. So basically about 2/3 of the length of the log, that bank downstream of that log will be protected by having that log facing upriver. If that log is facing downriver, that water is going to strike that log and it's going to turn directly into the bank. So then it's going to immediately start eroding that bank on the downriver side. It's almost counterintuitive because the log facing upstream is the good log, the log facing downstream is the bad log.
All right, thank you very much. But how do you balance the recreational aspect when you get into larger rivers like this?
You have to, look
Logs,
at the,
logs can be a hazard to canoers or kayakers and stuff like that.
correct. And so you have to look at what the, A, would never put logs in that basically would be hazardous. Managing ones that are there, are they sweepers? Are they potentially, do they have a hazardous condition there? If you're doing a restoration, you basically may wind up coming in and using rock instead of logs when you're doing with a river that has a lot of kayaking and stuff like that, because they have a tendency to have less problems with catching people or catching equipment, that type of thing. You kind of have to work your way backwards out of it. Part of it is working with whatever the user group is that basically is using it and getting some response and points from them. It's all you can there's a wide range of work you can do, and it depends on what the river needs and what the uses are in order to basically try to maximize each one of them. There's no easy answer.
Thank you. I appreciate it. Very nice presentation.
Thank you.
If anything else comes to mind, feel free to jump in at any point now, but you're welcome to email me and I can always get in touch. And Joe, if you come up with a question later on tonight when you're laying in bed, we will do our best to answer that for you. But does anybody else have anything they'd like to add?
Thank you, Joe, so much.
Very welcome.
Thank you, Joe.
Yes, thank you.
Thank you all for
All right,
coming.
I'm going to sign off.
Have a
I'm
great
going
night.
to
Go
sign
get some
off.
dinner.
Thank you, Christy.
Thank you guys.
Bye-bye.